Can you hear me?
Yes, yes, we can hear you.
What happened?
We can hear you, Father.
Hello?
We can hear you.
Ah, but I can't hear you.
Hello, hello,
That's strange.
hello, 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 hello,
Hello,
hello,
hello, hello.
hello.
Can you hear me?
Yes, but your microphone is not working.
Hello.
Hello, yes, Father, your microphone is not working. We are getting the audio from the laptop or computer, not from the microphone.
Hello? Can you hear me now?
Yes,
Hello?
clearly. Yes, we can hear you.
Same problem. I'll just log out and log in. One sec.
Okay, fine. Good. Thank you so much.
Come. No, I'm trying to enter onto a Google Meet. Now, hello, can you hear me? Hello? Hello?
Yes, Father.
Yes,
It's
Father,
showing.
we
We
can
can
hear
hear
you.
you.
Oh, Okay,
We
now
can,
this is
yes, we
option
can hear
number
you,
three.
Father.
Okay, thank you. Yeah. I am trying my other system. I have a technical expert here now. Let me see. My computer has some problem. Let me just check. This is a standby. I am listening. When you are ready, you start. I am ready here.
Okay, Father.
Then, okay. And hello, hello, hello. No, there
Hello,
is
sir.
no.
Yes, Father.
Can you hear?
Yes, Father.
Okay,
Yes, yes.
okay. Now let me go out of this. Now, can you hear me?
Yes,
Fine. Is this better?
yes. Much better, Father.
Okay. So we are set. I'm okay now. Now let
Yeah.
me just
We
do
are
this.
waiting for the speaker to join.
Fine.
Welcome, sir. Professor Baruah. Can
Hello.
Good morning,
yes.
Professor Sir.
Good morning. Good
Good
morning.
morning, sir.
Good morning. Dr. Sen.
Yes, sir, it's me, Debrishan Gupta.
Yeah. Okay.
Uh, Welcome you, sir.
So, yeah. So, when are you going to start?
Now only, we were just waiting for you. So
We
our
are just waiting.
principal will be starting with the welcome address and followed by your
Okay. So,
lecture.
let me check something.
Yeah,
Let me this share the screen. Okay.
Yes,
yeah,
yes.
sure, sure.
Okay.
Okay, so
Is it coming?
Not yet,
uh,
sir.
not yet.
Just
Excuse
And this.
is it coming now?
Not yet, sir. So there is a present now button on that one.
Presence. Hello.
Yes,
Yes,
it
sir.
is
It's
coming.
coming. It's coming.
Which one is coming? The story
Uh,
of pi.
yes, sir. It came.
Yeah. Title is coming.
Yeah.
Yes, story
Yes.
of pi.
Okay. Okay.
Okay.
So am I visible? Am I visible? My video.
Your video is uh, mm, yeah.
Yes.
Uh,
No, no.
no, sir. Only your screen is visible, sir.
Only
Yeah.
your screen is visible.
Okay. So when I will present, actually my
Hmm.
video will not come because I have a problem in the
Yeah.
iPad. Huh? Okay.
Okay.
But this screen will come. Huh?
Okay.
So
Okay. Okay.
if I okay stop this screen, then I think
Your video will
uh,
come. Yes.
yeah.
Your
Is
video
it
will
coming
appear.
now?
You have to stop presenting, sir.
Yes, sir. It is coming.
So now your webcam should be on.
Excuse-
Yes.
Yes, sir. It's
Now it
coming.
has come.
Okay, so that is the problem. And that means I cannot share the video while talking. Okay,
Okay,
Okay.
sir. Okay, sir.
So
okay. So
yeah.
now
Okay.
it's open, so you can start actually.
Okay. So good morning and welcome to everybody present here. I hope all of you are safe in these pandemic days. As this pandemic changed the usual course of physical teaching learning procedure, we find ourselves shifting more towards the online mode. Now, in that process, this is our first endeavor from the Department of Mathematics to organize a webinar. Now, with these few words, I invite our principal, Father Professor George Tharathil, for his welcome address. Welcome.
Uh,
Over to you, Father.
Thank you, Subhajit Paul, and thanks to everyone in the department. Congratulations for this first initiative, and I'm sure this is just the beginning of the count. And welcome, sir, to Nayandeep Baruah, of the expert and the resource person for today.
Thank
And
you.
sorry. This is a very interesting topic, the life of pi. And of course, as a class 8 or 9 or 10 math student, I remember hearing about pi first time. After that, I shifted from to arts and into philosophy. But last year, when there was the ISER coming for faculty training for science teachers on the campus, at the end of the program, they gifted me with a clock. It is the Pi clock. So ever since it has been, since I came down to Siliguri, I had promised to the department, and as soon as they get their new department space, this timing instrument also will reach them. Now, seeing it day in and day out made me curious. And of course, we have the classic of the story or the history of pi by Peter Beckman. If you will acknowledge that to be a classic text. And of course, the BX formula, which gave me an insight into how pi is being used in order to measure uh, space. So now I regard mathematics as the mother of all sciences because maths provides the tool for measurement. And wherever there is measurement, there is time. And wherever there is time, the question arises, against what do you measure time? What's the measuring yardstick? I mean, of temporal, the temporality. So the temporal and the here and now gets measured against that which has no beginning and no end, which we in philosophy call as the eternal, or in the mathematicians' language, the infinity. So I guess the pi goes back to the zero and to the half on the left and the 1 on the right of the horizontal axis. Though it is not still clear to me why it has to be on the right side 1 and half on the left and not the other way around. Or why the three quarters should be at the bottom half, the southern direction, if you are looking like a compass at this clock that I have, and the quarter, one fourth, as the horizontal axis upwards. These are, of course, my kind of queries, which probably in the process of discussion you will satisfy these basic fundamental queries of mine. But coming to the fundamental understanding of measurement as being the unit of science, of classification, of of deciphering, of analysis, whether it is statistics, whether it is physics, whether it is even geography, or one could even expand to say even in education, how do you measure, for example, benchmarking? So there seems to be a whole lot of ramifications developing from this sense of the measurement, which brings us, I mean, as I see, to this story of pi. And I'm eagerly looking forward to listening and being enlightened. Unfortunately, for a little bit of the time, I have to excuse myself to give another introductory talk to another webinar that is being organized. But, sir, welcome, and welcome to all the participants. And I'm sure this is going to be indeed an enlightening and enlivening time, as our own motto of the college states, to be like a flame that shines bright and that disseminates light. So over to you, sir, and to the story of pi. Thank you.
Thank you, Father. Thank you for your philosophical approach. So I now request my colleague, Assistant Professor Mr. Devdut Sengupta, to introduce today's speaker to the House. Devdut?
Am I audible to the house? Hello.
Yes. Yes.
Okay. First of all, I would like to thank Professor Deka Baruah sir for uh, take our invitation within a short period of time and consider this topic, which will be very much interesting to all the speakers. And secondly, I would like to thank our principal, Father Professor Dr. George Terratil, for motivating as well as encouraging us to do this kind of webinars. And as Father said, it will be more to go, so we'll look forward to that. And now I'm going to introduce Professor Nayandeep Deka sir, who is currently chairing the professor position in the Department of Mathematics, Tezpur Central University, where he where he joined as a lecturer in 1997, but from 2007 onwards, he is being professor in this Tezpur Central University. And sir completed his PhD from Tezpur Central University itself in 2001, and the title of the thesis is Contributions to Ramanujan Shapley type modular equations, class invariant theta functions, and continued fractions. Now, and Professor Deka Baruah sir completed his postdoctorate from University of Illinois, Urbana-Champaign, USA, under the Boy Scout Fellowship sponsored by DST, Government of India. Some of his achievements are: he got Professor M. Venkataraman Best Paper Presentation Award by the Ramanujan Mathematical Society in the 15th annual conference held at the Ramanujan Institute. Secondly, he got Young Scientist Award in the section of Mathematical Sciences by the Indian Science Congress. And as I said earlier, he got Boy Scout Fellowship in 2005 to 2006, under which he completed his postdoctoral degree. Some of his research interests are number theory, special functions, Ramanujan's mathematics, especially elliptic and theta functions, modulus equations, continued fractions, Q series, and partition theory. Under his guidance, 12 students has completed their research, PhD degree, and currently 2 people are doing research work under his guidance. He has published several papers in both national as well as international journals. He has been appointed as a reviewer for so many international and international journals, mostly by the Elsevier and so on. And I personally like number theory. So now over to you, sir. Guide us through the story of pi. Thank you all. Thank you, sir.
Okay.
Uh,
So thank you so
thank
much.
you, Deepak.
Hmm.
Yeah, sir, over to you,
Okay.
sir.
So thank you so much, Fodder, and Devdutt Sengupta, for your kind invitation for this webinar talk. And in fact, he invited me for the last 2 years, but due to some personal reason, I could not visit your college. And I'm hopeful that in future I will be able to do that. But anyway, so I'll be talking about pi, and so I'll share my screen, but due to some technical problems, when I share my screen, my video will not be visible. So excuse me for that. Okay, so I am going to share my screen. Is it coming? Hello.
Yes, sir. Yes, sir. It's coming.
Oh,
It's coming,
okay.
sir.
Okay, so some of you should be online because I may have to check
Yes,
whether
yes,
my
yes.
video is coming. If there is any problem and if
Hmm.
some sound is it is
Yes, sir. We
breaks,
are there.
then please tell me. Okay.
Okay, sir.
Yeah,
We are there.
sure, sure.
So so I'll be going to talking about the story of pi, and this is known to everybody actually. They have heard, the general public also, they have heard about pi. Okay, so what is pi? So let me just briefly tell you. So if we take a circle, maybe a, okay, so this circle is not, let me draw a circle. Okay, and the diameter, then one small circle, okay, and another diameter I take. Then, so let this circumference be C1, the bigger one, and diameter is D1, and here it is say C2 and D2. Then the ratio, this C1 over D1 or C2 over D2, okay, these two ratios are same, okay, whether the circle is bigger or smaller or whatever shape, okay, whatever this length of the circumference, this ratio is always constant, and that is denoted by pi. But this symbol is a very late comer in the history of pi, so I'll be talking about that when it was first used. So so this is pi, and from our school days, almost everybody knows that, yeah, the approximate value of pi is approximately equal to 22 by 7. 22 over 7, but 22 over 7, this is not equal to pi, this is approximate value of pi, because 22 by 7 is a rational number. This 22 by 7 is a rational number, but it has been proved that this pi is what? This is irrational. This is irrational number, so they are not equal, but 22 over 7 is a rational approximation of the irrational number pi. Okay. So 22 by 7 is a rational approximation. Okay. So, and this is quite popular because this constant pi immediately evokes a special kind of interest and response, okay, and even among the general public. And it also appears in several other contexts, such as movies or movie names, as you might have enjoyed Life of Pi. So, and there are poems on pi. There is a Pi Day and there is a place of pi in Guinness Book of World Records. And there are so many places where pi appears. In every branch of science, uh, it appears. So, and in mathematics, it already there are so many topics where pi appears, but in other branches of science also it appears. So in this talk, a few of those interesting tidbits, along with a brief discussion of the various methods of calculating the digits of pi, will be discussed, because I already told you that pi is irrational. So the decimal expansion of pi is, in fact, this goes to infinity. That means you can find as many as digits as you can. But how these digits were found? What are the different methods? So that I would like to discuss, and other tidbits I'll be discussing. And this is one of the most popular constants in the science, and therefore this is also known as the king of constants, king of mathematical constants. Okay, all right. Just a minute. So I have some problem here. Just a minute. 6. It's not working. Just go to. Excuse me. Okay. Okay. So now, so let me say something about Pi Day first. So this is interesting to everybody. So you see that March 14 is Pi Day. March 14 is Pi Day. Yes. Because March 14 is written as 3, like this, 3 oblique 14 in Western countries. And the value of pi is actually 3.141, etc. So therefore the first two digits are this one 3.14. So therefore March 14 is observed as Pi Day, and this is very popular. And in 2019, UNESCO adopted March 14 as the International Day of Mathematics, and from 2020 onwards, this day is also observed as International Day of Mathematics. But the celebration of Pi Day was started at San Francisco's Exploratorium in 1988 by Larry Shaw. So he was the curator of the museum. So he started the Pi Day on March 14 in 1988. So you see that Larry and his colleagues, they were taking a procession out where the value of pi, these posters of value of pi are there. So 3.141, etc. Okay, he is Larry Shaw. Okay, so to popularize the constant pi, and because it involves many things in the study of pi, many things are involved, and almost most of the great mathematicians are involved in evaluating the value of pi and other formulas. So therefore, Larry thought that it would be a fitting tribute to them to celebrate for March 14 as Pi Day. And in fact, so UNESCO adopted this as the International Day of Mathematics. From this year onwards, we are celebrating that. And in fact, possibly for the first time in Assam, maybe in India, I do not know whether Pi Day has been celebrated before this. So we celebrated Pi Day in 2008. Okay, so I was inspired by Larry Shaw. Okay. So this is the first page of our flyer on Pi Day. So we had what, your Pi Day cake. So we had this Pi Day cake, then Pi Day song, Pi Day procession, etc. We had such things, and we had a recitation.
Hello, sir.
Uh, his
Sir.
connection suddenly dropped. His connection suddenly dropped.
Yes, yes. Wait for a
Uh,
minute then.
yeah.
Okay. Otherwise, I'll call him. Wait a minute.
Hmm.
Yeah, I think the Devdutt, you have to call him, okay?
Wait for a minute, sir. 1 minute, just. I guess he
One
will
minute,
try to.
1 minute. Okay, okay.
He knows, I guess, that his connection is lost. He will be trying.
Yeah, Devdut, please call in. Hello, Devdut. Hello, Devdut. Probably he's calling. Yeah, he has come back. Hello, sir. Can you hear us?
Hello.
Hello, Baruah, sir. Hello, Professor Baruah.
Sir,
Hello.
probably disconnected.
Hello.
Probably.
Yes, 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 sir.
Now.
So it was suddenly disconnected.
Yeah,
Okay, so let me share it again.
yes,
Okay.
So
please.
okay, so sorry. It's, hello.
Yes,
Yes, sir.
Is it
we
coming?
can hear.
Yes, sir.
Yes,
It's coming.
So where I left, this one was available previously.
the flyer of your Pi Day. Yes,
Yes.
over
Yes.
here.
This
Yeah.
one.
So
This one.
this is the first phase of the fire. So we had some
Yeah.
activities there. So I was talking
Hmm.
about that, and we had a recitation competition and other competitions. So I just want to say, so this is the our Pi Day cake. Huh? So we had a cake, Pi Day cake. Then we had some Pi songs like this: Happy Pi Day to you, Happy Pi Day to you, Happy Pi Day to you, etc. Okay. So we cut the cake, and there was an exhibition on Pi formulas, and there was a Pi Day procession. So this was just to encourage the students, school students, and university students, so that they know about Pi. Okay. And this was conducted in 2008. Okay. And this is the old university gate, old gate up. So we assembled there, and we had a procession there. Okay. Then we had Pi recitation. There are some. These are some competitions. Recitation from memory. So how many digits one can remember? Okay, so we had a competition like this, and another participant, school students. So school students, and we had some pi symbol making competition because the pi symbol, this is very beautiful. So in how many ways, or in how beautiful way one can this make this pie. Okay, so this is a fruit pie. So this is fruit pie made of all fruits. Then this is flower pie, so made of flowers. Then this is abstract pie, some abstract art is there. And this is salad pie. So you see that these are all salads, cucumber, then tomato, etc. Okay. Hello.
Yes,
Yes, sir.
sir.
Hello.
We can hear.
We can
Yes,
hear
Can you
we
you.
hear
can
me?
hear you.
But
Yes, it is coming.
hello.
Yes, sir.
Yeah,
It's
it is
coming.
coming.
Which one is coming?
So not yet
The
showing, but
screen
it
broadcast.
screen broadcast.
Screen broadcast.
But I'm not able to. Is it coming now?
No, sir.
No.
Yes,
Yeah,
sir.
it
It's
has
come.
come.
It came.
Okay. Ah, all right. So this is another. This is you can say that dal pie. So it is made of dals, masoor dal, then moong dal, etc. Hello.
Yes.
Are you seeing my screen?
Not
It,
right now. It was visible, but not right now.
I don't know how. What is the problem here?
Hello, Subhadip sir.
Yes, sir.
Sir could share the entire screen and then he can change over to any
Yeah.
yeah.
Uh, Yes,
It's
this
coming.
works.
It's coming.
Again, this is screen broadcast.
Yeah, so Subhajit sir, please tell him.
Uh, Sir, your screen is coming. I think you need to start the screen broadcast. Hello, sir.
Hello.
Yeah. Uh, you you need to start your, yeah.
I don't know. It may be network problem. Is it
Your
coming
your
now?
Yes,
yes,
it's
yes,
coming, sir.
Okay.
yes,
So this
coming.
is another this pi symbol made by the small school students. And we had another pie eating competition. So these are American pies, you can say. Like PIE. This is not actual mathematical pi. So this is eatable pie. So there are some competitions on pi. Then in the next year also we followed this in 2009. So this is our cake, and this is better than the previous year. So you can see that this happy pi is written over here, and the digits are written over here. Okay. So and again the winners of pi eating competition of 2009. Then this is the winner of pi symbol making competition in 2009. Okay, so you see that the beautiful pi has been made. So this line and this one. Okay, so and there are actually 4 person because one was there to lift the third one. So they are the BTech students of our university, and they are now well placed somewhere. Okay, and this Pi Day is so popular nowadays. For example, we have seen. I want to say that on March 14, 2018, in Sultan School, Muscat, Oman, this is the longest human representation of pi digits. 1,182 people were there to make the pi. This 3.141, etc. Okay, so and in last year 2019 in UK, so this is the record for the largest human pi symbol, 1170 people. So all these are there, all these people they made a pi symbol. So then why we need this pi? Okay, so and we have that various Babylonians and Egyptians, they estimated pi, the value of pi is approximately equal to 3, and this is 3 and 1/7, etc. So they tried to find the value of pi because they knew that if the circumference is, if the diameter is something and circumference is something, then this is circumference is C is almost 3 times of diameter, and 3 and something plus. Okay, so what is that plus? How many more? What is the difference between this one, 3 and that? Okay, so that they wanted to evaluate, and there are some evidences for that. For example, there are some clay and stone tablets where you can see different formulas, mathematical formulas, and this was actually about 2000 BC. So therefore, pi has been studied almost for 4,000 years, and still some serious researches are going on the value of pi and the properties of pi. Okay, so this has been studied the, since 4,000 years, right? So and in pyramid also, Egypt's pyramid, Rin papyrus. So they found a papyrus. This is papyrus, and there are so many formulas are there, mathematical geometrical constructions were there, and one can find the value of pi. There are some pi formulas in those papyrus also. So in Bible also this pi is mentioned. For example, in Bible Old Testament, 1 Kings this version and 2 Chronicles 4th. So this was written. Also he made a molten sea of 10 cubits from brim to brim, round in compass, and 5 cubits the height thereof, and the line of 30 cubits. So you note the here quantities here. 30 cubits, 30 means this round is 30, and 10 qubits is brim to brim. So here, so therefore this is C and this is D diameter. Okay, so by Bible we can see that this is pi equal to 3 because it is 30 and this is 3. So this in Bible it is approximated, the value of pi has been approximated as pi equal to 3. But later on, it was also some of the scholars, they noted that actually it was not extremely circular. Okay, this brim was not very circular, so therefore the estimate was 3. Okay, and in pi in India, so there are many these mathematicians who tried to understand the properties of pi, and one of them was Aryabhatta. All we know about Aryabhatta. So he wrote a book, Aryabhatya, and in one of his this chapter, so he written this Sanskrit shloka. So this is the shloka, Aryabhatta's. Chaturadhikanga shatam ashtam gunama dvasastisthata sahasranama, etc., etc. So this is in Sanskrit. So what is the meaning? The meaning is that this is the meaning. So by adding 4 to 100, that means Saturadhikam Satam. Okay, Saturadhikam Satam, 104, multiplied by 8, Astam Gunam, multiplied by 8. With this 62,000, that means Dvasastis Tata Sahasranama. So 62,000. So this is the formula. 4 plus 100, Saturadhikam Astam Gunam into 8 plus 62,000. That is the circumference of a circle having diameter 20,000. Okay, so this was Archimedes' formula, Archimedes' shloka, sutra. So by using this, what we get? We get 3.1416. Okay, but what is the actual value of pi that we know today? That is nothing but 3.14159265358, etc. And what is Archimedes' value? 3.141. So you see that 3.141 and it is 3.141, these are same. And this is 6, this is 5. So therefore, up to 3 decimal places after the decimal point, Aryabhatta found the value of pi. Okay, and all were written in shlokas. But the first mathematical method of evaluating the value of pi was given by Archimedes. This is the first, what is called iterative method. First iterative method. That means one can iterate the steps and find more and more digits of pi. And in fact, Archimedes, he calculated the value in between 287 BC and 212 BC. Okay, so what is Archimedes' method? So let me just briefly discuss his method. This is mathematical method. So, here, so he took a circle, and you take the diameter is what? Diameter is 1. This diameter is 1. Circle's diameter is 1. Okay, so this perimeter is C, so diameter is 1. C by 1, so C. So length of the perimeter, that means circumference will be what? Circumference will be this circumference will nothing but what? That is pi, the value of pi, because diameter is 1. Okay, so then what he did, he inscribed this one as inscribed like this. Inscribed hexagon he took a inscribed hexagon like this. So this is his inscribed hexagon, 1, 2, 3, 4. So my this regular hexagon is not very correctly drawn, but you can see that this is a hexagon, and he found the perimeter of this hexagon. So this is the perimeter of this. Then he circumscribed it. So this is another hexagon, regular hexagon, circumscribed. So he circumscribed like this. Okay, that is outer hexagon. This is the outer hexagon like this. So therefore, you see that if this is the outer hexagon, C0 is the perimeter, and your CI is the inscribed hexagon perimeter, and your C will definitely lie between what? CI and C0 from here. Okay, so therefore your pi, this C is nothing but what? Pi. So pi will lie between the perimeter of the inscribed hexagon and the outer hexagon, circumscribed hexagon. Okay, so he did it, and he found that is actually pi is in between 3 and 2 root 3. So he concluded that pi lies between these two. Then what was the innovative method about Archimedes was that, so from a circle like this, Okay, from circle initially it was hexagon, but he can double the sides of the polygon. That means from this hexagon, he went for the perimeter of 12 gun. So 12 gun. That means he doubled the sides. So initially there were 6 sides. Now he took another, this sides took what? He took these sides. From one side he got 2 sides. Okay, and from this side he can calculate this side. Okay, so therefore he can calculate the perimeter of these 12 guns now, regular 12 guns. Okay, and the outer 12 gun. Okay, so again outer 12 gun also he like this. But you see that when you take from 6 to 12 sides, your this inscribed polygon, it goes nearer to the circumference. Okay, so therefore it will approximate better than the hexagon. Okay, so he found that. Right, from 6 guns, so he went to 12 guns. Okay, so then 12 to what? 24. Then from 24 to 48. Then 48 to 96. So he doubled the sides 4 times. Okay, and he found the value of this. He concluded that. So he arrived at what? 4 times. Doubling 4 times, he arrived at this one. Doubling 4 times, he arrived at this value. That pi lies between 223 over 71 and 22 over 7. Okay, but what is the left hand side? 223 over 71 is 3.140845 and this is 3.142857. So pi lies between in these two, but you see that the first two decimal places are same. It is 3.14, this is 3.14, and pi lies in between them. So therefore pi, the value of pi must be approximately equal to 3.14. So therefore, up to 2 decimal places, we can find the value of pi by this, but by doubling 4 sides. And this was a very popular method. If you double it more times, then you get more and more these digits, more and more correct digits. Okay, and this is a self-correcting type digits, because in the next step you will get at least another 1 or 2 digits correct. Okay, etc. And this was used by many mathematicians from many countries, and the famous was calculated by Ludolf von Schulen of Germany in 1610. So towards the end of his life, so he calculated 35 decimal digits of pi, and his value was actually engraved in his tombstone, but it was lost, and in the year 2000 it was again it was reconstructed, and you see that the value of pi has been written here, the value of pi up to 35 digits. So this is written here. So this is Ludolf's tombstone. Okay, and so that was about the first method, that is Archimedes method. And in the meantime, there were some notable infinite formulas for pi. So that means pi has been connected to other mathematical these concepts, for example, square root and infinite product, then infinite continued fraction, etc. And the most famous one is given by Franco Vieta. This is the first infinite product given by Vieta in 1593. So 2 over pi is square root of half, and square root of half plus half, and square root of half. So this is not very tough to prove it by trigonometric functions. One can easily prove that. Similarly, there is John Wallis formula, 1655. He gave a formula for pi over 2, which is infinite product. And here, and again, Lord Brouncker, he was the first president of Royal Society. So he gave the value of pi in the formula for 2 by pi in terms of what? Continued fractions. So this is a continued fraction. The fraction is continued up to infinity. So therefore, this is an infinite continued fraction. So this is a famous infinite continued fraction representation of Lord Brouncker. Okay. So our Isaac Newton, he himself calculated the value of pi by using his new discovery of calculus. As you know that Newton and Leibniz, they discovered this calculus. independently, and there was a fierce battle between Newton and there's a debate in between Newton and Leibniz. Okay, so actually who invented this or who discovered this calculus at first? So Newton himself used this integral formula, integration, definite integration formula, to write pi as an infinite series. Okay, and he calculated the value of pi up to 15 digits. But later on, he confessed that I am ashamed to tell you to how many figures I carried these computations, having no other business at the time. That means he was not very happy in his calculations, because having no other time, so no other business at the time, he could calculate only up to 15 digits. Okay, he could not go beyond that. So we know that this calculus this is discovered by Newton and Leibniz. And so that came our second method using calculus. So Gregory, Leibniz, and Madhava series. Okay. So in 1671, Gregory gave a series of 10 inverse of x, and that is arc10 of, this is also called arc10 of x. So arc10 of x has this definite integral, okay, and one can expand in terms of infinite series. So arc10 has this infinite series, and in this series, if I put x equal to 1, if we put x equal to 1, then it will be what? 10 inverse of 1, or arc10 of 1, and we know that the value of arc10 of 1 is nothing but pi by 4. So therefore, if I put x equal to 1 here, so here it will be 1, then here it will be 1 minus 3 plus 1 by 5, okay, then minus 1 by 7 plus etc. So we'll get an infinite series, and that was actually given by Leibniz. This is Leibniz series. And but interesting thing is that they developed this in 17th century. So you see that 1600 something. So it is 17th century. But in India, in Kerala School of Mathematics, headed by Madhava. So they actually knew this. So in 14th century. So you see that how developed Indian mathematics was there at the time of 14th century. Okay, so they knew, or they knew how to prove this type of infinite series. So therefore nowadays these are called Gregory, Leibniz, Madhava series. But all those were written in Indian languages, so it never went to the Western countries as expected. Okay. So this is another very interesting thing about this Leibniz series. So I just briefly want to mention it. Okay, so you see that when this is Leibniz series, so if you truncate somewhere, then you will get the value of pi. But it is very slowly converging, right? Because the denominators are just increasing by 2, odd numbers and increasing by 2. That means it is just 3, then 5, 7, etc. And also there is plus minus, plus and minus, plus minus, etc. Okay, so therefore so you see that pi over 4 equal to 1 minus 1 by 3 plus 1 by 5 minus etc. So pi equal to what? 4 times of this series, 1 minus 1 by 3 plus etc. Okay, so so if I truncate this in say 5 lakhs, so 5 lakhs. Okay, we truncate this in 5 lakhs. That means Leibniz series, we truncate it at 5 lakhs. Okay, then this beautiful phenomenon was observed by Roy Nott. What is the phenomenon? So you see that it is 3.14159. This is 0. And next one is 65358979. And again, this is 40, but this should be 38. This should be 2. Okay, etc. All right. So therefore, there are some mistakes in, there are some differences in actual value of pi. And what are the differences? This is differences 2, 38, etc. Okay, so but all these are correct. All the others are correct. That means in between digits are correct, but these are not correct. 0 and 40. Similarly, these red colored digits are not correct, but all these are correct. Okay, so this is a very special, interesting fact. Okay, and that was observed by Roy Nott, and he asked Jonathan Borwein, Peter Borwein, and Carl Dilcher, so how to explain that. And they actually explained this in terms of what is called Euler numbers. Euler numbers is what? So this is an even function. You see that secant of z is an even function, right? and so it is analytic at z. So it has a tail. It is a Maclaurin series expansion about z equal to 0. That means in terms of z power, I can write. So it is z to the power twice k, because the function is sec z is what? Even function. So therefore your z to the power twice k will come, and there some coefficients are there, and these coefficients are called e twice k. These are called Euler numbers. Okay, so these can be explained through Euler numbers. Okay, so I leave it to the students to think about that. Okay. Then in 1699, Abraham Sharp, he calculated 71 digits of pi by using another Gregory Madhava type series. And what is this? He put x equal to 1 over root 3 in Gregory's series. So in terms of x, if I put 1 over root 3, I remember that Gregory series is convergent for modulus of x less than 1. So if we put this one, and I know that tan of 30 degree is 1 over root 3. Okay, 10 pi by 6. 10 pi by 6 is equal to 1 over root 3. So therefore, tan inverse of 1 over root 3, arctan of 1 over root 3 is nothing but this infinite series. And if we truncate somewhere and calculate these numbers, okay. So in that way, Abraham Sharp found 71 digits. And next, John McKean in 1706, he calculated 100 digits by using again the McKean type, this Gregory Madhava Leibniz type arctan series. Okay, so this one can expand. This is the expansion of this pi equal to this one. Yes. Okay, so one can expand arctan of 1 by 5 as this, and expand this in terms of this. Okay, so therefore, if you truncate suppose up to 50 terms, then one can find the value of pi. Okay, rational approximation of pi. Right. So in that way, John McCain, he calculated 100 digits in 1706. Okay. And William Jones of England used the symbol pi for the first time as it was used today. So before that, the people, they used different symbols for denoting the constant pi. Okay, so only in 1706 William Jones used. Actually, he was a science writer and he was reporting about McCain's 100 digits calculation. Okay, so it is a very late cover in the history of pi. Only in 1706 this symbol pi was used to denote the ratio between circumference and diameter of a circle. Okay. And in 1761, one landmark was achieved, and what is that? That Johann Lambert, he proved that pi is irrational. Okay, so pi is irrational, and we know that any rational number a by b, where b is not equal to 0, this has a what? Decimal expansion, and not a2, a0, say a1, a2, etc. So this is the decimal expansion, and that will be always what? Either it is finite or it is a recurring decimal. For example, 1 over 2 equal to 0.50. It is 0, all 0, 0, 0, 0, etc. So this is finite actually, I can say. It is 0.5. But 1 by 3, this is infinite decimal expansion. But though it is infinite, but it is what? It is recurring. That means 3 is recurring here. But all irrational numbers cannot have any infinite recurring. So it must be infinite, and what? Non-recurring. So that means your pi cannot have any pattern 3.141596, etc. So there is no any period of repetition here. Okay, so that has been proved in 1761. So therefore, the value of pi can be calculated as many digits as you can, but only the problem is that the suitable method. Okay, so how fast converging methods one can use. If we have supercomputers also, then it may not be possible to after a certain limit. Okay, so it has some limitations. So therefore, more and more sophisticated formulas and sophisticated way of calculating the value of pi is required. Okay, so and in 1882, Ferdinand Lindemann proved that pi is transcendental. And what is a transcendental number? So note that your root 2 is irrational. We already know actually. That is, in school we proved that root 2 cannot be what? A by b form, where b is not equal to 0. So this is a proof. By using fundamental theorem of arithmetic, one can prove it. But your pi is not, pi is irrational, root 2 is also irrational, but root 2 is algebraic. Root 2 is algebraic number. Because root 2 is a solution of what? X square minus 2 equal to 0, an algebraic equation. So if we solve this, one of the roots is what? Root 2. But pi is transcendental. So you cannot get any your a0 plus a1x plus a2x square plus etc. and an xn. So any nth degree polynomial, you cannot get pi as a solution. Okay. From an algebraic equation, one cannot get the solution of pi. Okay. So therefore, pi is transcendental. Similarly, another transcendental number is e. The well-known e, constant e, is also transcendental, and that is proved in 1853 by Hermite. Okay. And there are some more Makin type formulas. So this, so let me just, okay. So these are three Makin type formulas. This one, and this one. Okay. And the other one was Makin. The origin formula was Makin in 1706. So pi by 4 equal to 4 times of 10 inverse 1 by 5 and minus 10 inverse 1 by 239. So this was. So there are these 4 Makin type formula where there are 2 10 inverse. Here 1 10 inverse, another 10 inverse, 10 inverse, 10 inverse, 10 inverse, 10 inverse. There are some coefficients here, but these are the only four Makin type formula having 2 10 inverses like this. Okay. So, but there are some more Makin type formula for 3 terms. Similarly, for 4 times, 5 terms, etc. So there are many Makin type formula, and in each of the Makin type formulas, one can expand this by Gregory, Leibniz, Madhava series and find the value of pi by using this. Okay. So this is one, the big one. This was found by Arndt in 1993. Okay. So in 1844, Johann Zacharias Das, he calculated 205 digits by using this Makin type formula having 3 terms. Okay, you expand this by using Gregory's formula, and one can find the value of pi after truncating the infinite series to a finite number. Okay. So I leave it. Dash was like our Shakuntala Devi. So Dash demonstrated his computational skill by multiplying this into this in 54 seconds. 2 20-digit numbers in 6 minutes he can multiply in his mind. 2 40-digit numbers in 40 minutes. Okay. 200 digits number in 8 hours 45 minutes. So he was like our Shakuntala Devi. So Gauss requested that Dash be permitted to assist him, but actually Dash died shortly afterwards. Okay. And in 1873, William Shanks computed 707 decimal places by employing Makin's formula. So all these calculations were done by Makin type formulas. But D.F. Ferguson in 1945, he found that actually Shanks' value is wrong after 527 decimal places. Okay, so and Ferguson actually calculated up to 530 digits, and it was extended again in 1946 to 808 digits. Okay. And in 1949, Smith and Renz computed 1,120 digits. Okay, so these were done by mechanical calculators, mechanical calculators. So calculators, but formulas are same, all Makin type formulas. So no new formulas are there. Formulas are same, but the calculating devices were different. Initially, those were hand calculated, but now mechanical calculators. Then you see that in, so can you guess it? So this is a picture of a computer, and that computer is nothing but the first electronic computer, and yeah, electronic numerator, integrator, and calculator. Okay. So this is the first electronic. So how big you see, how big this ENIAC was. Okay. So, and in fact, you can see that. So let me, okay, so this one. So you see that ENIAC had 70,000 registers, 18,000 vacuum tubes, 10,000 capacitors, 6,000 switches, 1,500 relays. And ENIAC was 10 feet tall and occupied 1,800 square feet and 30 tons weight. And ENIAC did only 5,000 editions per second, 5,000 editions per second. But in comparison to today's computers, it was very slow. But in comparison to hand calculations at that time, it was very fast. And so this was used to find the value of pi in 1949 by Metropolis Rittwitzer von Neumann. And they used Mason's formula on ENIAC to compute 2037 digits. And before that, the record was 1,112 by mechanical calculator. So it actually jumped twice after the use of computers. So then all people started using computers, and new computers were developed or built, and new records were broken. Okay, records were broken for the value of pi. These are some samples just. So 10,000 digits were found in 1958 by using IBM 704 computer. Then 1 lakh Sang Rance Jr. in 1961 by using IBM 7090 computer, 7090 computer. Then our third method came. Okay, so before this making type series method, so Sang and Rance, they computed 1 lakh digits. So you just remember that in 1961. And then our third method came. What is this third method? That is AGM and pi. So this is arithmetic geometric mean. What is arithmetic geometric mean? We all know that arithmetic mean of two numbers A and B is A plus B by 2. And what is the geometric mean? Geometric mean is square root of AB. Now, if I take arithmetic mean of this number and this number, okay, arithmetic mean of this number, and I will get another what? A1. And if I take the geometric mean, then I will get again B1. And I take the arithmetic mean and geometric mean of these two, A1, B1. Then again I take arithmetic mean and geometric mean of these two. Okay, so again I will get some A2 plus B2 by 2 square root of A2 B2. Okay, so this process you can go on. One can carry on, and we will find that this actually converges to the same limit. This arithmetic mean and geometric mean, the successive arithmetic mean and geometric mean, this converges to the same point, and that is called the arithmetic geometric mean. And this was discovered by Legendre and other people, but some beautiful formulas and the properties were studied by Gauss at the age of only 14. And some simple properties are like this. So arithmetic mean of lambda A in lambda B is just lambda will come out, lambda of AGM of AB, AGM of this is this, etc. Okay, so these are some simple properties, but many other properties were found by Gauss. Okay, by Gauss. What he noticed that actually he numerically calculated some arithmetic geometric mean. So arithmetic geometric mean of root 2 and 1 he calculated in his diaries. It was written. So this is root 2. So root 2 is 1.414, etc. This one, and 1 is this. So if we take arithmetic mean and geometric mean of these two, arithmetic mean will be this, geometric mean will be this. Now you take the arithmetic mean of these two. Okay, this and this. So we will get this one. And geometric mean is this one. Then again you take arithmetic mean, we will get this one, and geometric mean this one. Arithmetic mean, geometric mean. But you see that the interesting thing is that arithmetic mean and geometric mean at the first stage was same only up to 1 digit. But in the next step, it is 4 digits are same after the decimal point. 1981, 1981. Then in the next digit, it is more than twice of that. So there are four digits. Here there are 9 digits are same. You just consider the red colored digits. Other digits are not same, but red colored digits are same. So the 9 digits are. So here you see that more than 18 are same. So that means more than twice digits are same. So it is very fast converging series. So you see that 1, 2, 3, 4. 4 times iteration. This gives how many digits same. Okay, so it is a very fast converging series, and that fast converging series was used by Gauss to see some connections between elliptic integrals and other things. And excuse me. And he actually wrote from his in his diaries some formulas, but from those formulas one can get the formula for pi, and that was rediscovered in 1976. And you know that Gauss was born in 1777 and died in 1855. Okay, and he wrote this pi, the formulas connecting pi and other things in about 1800. Okay, so therefore in 1976, almost after 175 years, so Salamin and Brent, they found the actual pi formula involving AGM of these numbers. So pi is connected to AGM, arithmetic geometric mean. And where CK is AK minus BK, where AK are the arithmetic means, successive arithmetic means, and these are successive geometric means. Okay. So can I get some water, please? Hello?
Sure, sir.
Okay, just
Yes, sir. Yes, sir.
Yeah, sure. Please,
Yes.
please.
Okay, sorry for the interruption. Okay, sorry.
Okay,
Yeah.
sure.
Okay. So that AGM formula can be put into an algorithm. So this is the algorithm. Initialize the initial points. A naught is 1 and B naught is this. So that means we are starting with the arithmetic mean this and arithmetic mean and geometric mean of A naught and B naught. So, and we do it successively. Okay. So after doing successively, you will see that your Pn, this converges pi quadratically. Quadratically means what? Each time your accurate values of those arithmetic mean and geometric mean will be doubled. This will be doubled. Okay. So that was quadratically converging series work. So successive iterations will produce 1 digit correct, then next 4 digit correct, 9 digit correct, then 20, 42, etc. So 1, 2, 3, 4, 5, 6, 7, 8. And the 8th iteration, 697 digits will be correct. So this is a very fast converging series. And these more AGM type formulas were developed in 1987 by the Baruah brothers. Jonathan Baruah, John Baruah, and Peter Baruah. They are brothers, John Baruah and Peter Baruah. In Canada, their father, David is also a very great mathematician. Okay, so they also found some algorithms. So this is quartic algorithm. This is Baruah's quartic algorithm in 1987. Quartic means what? It converges this quartically. It gives what? Pi quartically. That means in each iteration, the digits will be quadruples 4 times. If it is correct up to 3 times, 3 decimal places, in the next iteration it will be 12 decimal places. Next it will be 48 almost. Okay, more than quartic actually. So more than 48 digits. So it is another very good algorithm, and this is a very fast converging algorithm, and this is being used in many calculations of digits of pi. And in 1983, Tamura and Canada of Japan, they calculated over 16 million decimal places of pi. So you see that 16 million. decimal places of pi, using the algorithm, AGM algorithm, and verified by quartic algorithm, and verified by other those algorithms related to this AGM. Okay, then our Ramanujan came into the picture. Okay, so I will tell about Ramanujan. Everybody knows his this biography, but let me again say something on this. So he was born in December 22nd, 1887 in Erode, Tamil Nadu, and in his actually maternal grandparents' home, because that was the customary of at the time that the first child will be born in maternal grandparents' house. So after his birth, after a few months, they moved to their original home at Kumbhak. This is the picture of Ramanujan's mother, Kumalata Ammal, and there is no picture of his father available. So they moved to Kumbakonam, and this was approximately 260 kilometers southwest of Madras. And Ramanujan's family was economically poor. So this is Ramanujan's home at Kumbakonam, and this was pictured by Professor Bruce Bond in about 2000, in the year 2000 or so. So his family was poor, you can see that. And actually this house is now taken by Sastra University, and they have converted into a museum, converted this into a museum. And this is another house. This is a rented house in Madras, where Ramanujan actually rented this house while he was in Port Trust office. Okay. And in 1898, he entered Town High School of Kumbakonam, and he was a very brilliant boy, especially in mathematics. So he passed his matriculation examination in first class, and for that he received what? Subramaniam Prize, Subramaniam Junior Prize. So at the age of 12, Ramanujan borrowed S.L. Loni's Plane Trigonometry while he was in high school. So, and worked all the problems in that book, Plane Trigonometry. But though the book is Plane Trigonometry, but this also carried what? Calculus, infinite series, complex variables, etc. So therefore, Ramanujan learned these topics from that book and by doing the examples by himself. And at the age of 15, when in the high school, Ramanujan again borrowed from Kumbakonam College Library George Subriskar's A Synopsis of Elementary Results in Pure and Applied Mathematics. And actually, George Subriskar, this is a current edition, so which I bought from Amazon. Okay, so this picture is very peculiar, this book, because Carr was a tutor at Cambridge, and he compiled his formulas in this book. So about 4,417 results were there, and there were no proofs, almost no proofs, mostly without proofs. So the first formula was a square minus b square equal to a plus b and a minus b, this algebraic formula. And there are not only these, there are many more complicated formulas and integrals and geometrical problems, but almost no proofs. So Ramanujan worked on all these proofs, and also he discovered many other new results of his own. Okay. So, and after passing out matriculation examination in first class and with scholarship, he entered Government College Kumbakonam in 1904. But by that time, he was totally absorbed with mathematics. Okay, by reading Carr's book, he was fascinated by mathematics, and he only did mathematics during that time. So at the end of the first year, he failed to pass in the examination and lost his scholarship. So he's lost his scholarship. But Ramanujan's family was poor, so he could not again took admission at Kumbakonam. So 2 years later, somehow in 1906, he entered Pachayappa College, Madras. And once again, he failed his exams at the end of that academic year, because he would not study any other subject except mathematics. So he will only study mathematics, mathematics, and mathematics. Okay, and luckily we had Ramanujan's performance in that examination. So in English, you see that maximum marks were 200 and minimum required for passing is 70, and he got 38. So he failed. Okay, and in Sanskrit, maximum 100, minimum required 35, and he failed again, 34. In mathematics, out of 150, he passed with 85. Minimum was 45. And in physiology and history, he did not appear because he had some this health problem. Okay, so that is Ramanujan's educational qualification. Educational qualification was what? Your FA failed. FA failed. FA failed. Okay, so he failed in FA examination. Since his family was poor, Ramanujan was forced to terminate his formal education. Okay. But working in isolation, Ramanujan completely devoted himself to mathematics and continued to record his discoveries in his notebooks. And initially, Ramanujan, so this is one of the 2 pages of Ramanujan's notebook. And initially, he recorded his notebooks in a slate. Okay, in a slate. So luckily, we have this slate is preserved in Madras. Okay, but that is not actually public preservation. It is privately preserved. Okay. So, and in 2016, 7th August, I had the opportunity to hold this slate. So this is Ramanujan's slate, and I'm lucky that I got a chance to hold this slate. So, and this is the other side of the slate. And in 1909, Ramanujan married as Janaki, and Janaki was 9 years old. So without means of any financial income, so Ramanujan terribly sought for a job. But what was his qualification? FA failed. So who will get a job for him? Okay. So he went to meet V. Ramaswamy Iyer. He was the deputy collector of Madras Civil Service, and showed him the notebooks and asked him for a clerk's position. And Iyer was also the founder of Indian Mathematical Society in 1907. But Iyer thought that Ramanujan's talent would be wasted in a clerk's position and sent him to R. Ramachandra Rao. And he was also a mathematician and executive member of Indian Mathematical Society, and he was also collector of Nellore. So Ramachandra Rao also saw Ramanujan's notebooks, and actually he recognized Ramanujan's talent, and he temporarily gave some financial assistance to Ramanujan. Okay. But after a few months, Ramanujan declined to take that financial assistance, and after a few months, Ramanujan became a clerk in Madras Port Trust Office after the assistance of Ramachandra Rao and other kind-hearted people. Okay, and in the Madras Port Trust Office, there were 2 very kind persons. One was Chief Accountant S. Narayana Iyer, and Sir Francis Spring. He was the chairman of Ramanujan, the Port Trust. So they knew how talented Ramanujan was, and they suggested Ramanujan to write to British mathematicians, and they helped actually in writing the letters to British mathematicians. And initially, Ramanujan wrote to 3 British mathematicians, MJM Hill. He wrote to MJM Hill first, but Hill replied, but that was not very encouraging. And interestingly, Hill is from fluid mechanics. And then he again wrote to Baker and Hobson, but they actually did not reply. And all these 3 were very well-known mathematicians, and all of 3 were FRS. Okay. And there are some good books written by Hobson and other people. Okay. Then on January 16, 1913, Ramanujan wrote to G.H. Hardy, okay, the number theorist and the famous G.H. Hardy. So Hardy saw Ramanujan's formulas, and with a discussion with Littlewood, so he came to conclusion that Ramanujan is a genius. And even after some of his formulas sent by Ramanujan on continued fractions, not all formulas, but some formulas on continued fractions. So Hardy later on said that they defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true. If they were not true, no one would have the imagination to invent them. So Hardy recognized Ramanujan's talent, and he invited Ramanujan to Cambridge to work with him. But after initial reluctance, because if he sailed through seas, his caste would be lost. So, and there were some hesitance from his mother and other family members. But ultimately, after a lot of persuasions by Hardy and other British mathematicians who came to Madras for lecturing at the time, they persuaded Ramanujan to visit Cambridge. So therefore, on March 17, 1914, Ramanujan sailed for England, okay, to work with Hardy. And Ramanujan wrote some monumental papers, some of them jointly with Hardy. And Ramanujan became Fellow of Royal Society and Fellow of Trinity College in 1918. But unfortunately, at the end of third year in Cambridge, that means in about 1917, that spring semester, at the end of spring semester in May, so Ramanujan became ill. And most part of 1917 to 1919, he actually visited only the sanatorium and other hospitals in England. So, but when he partially recovered in 1990, he returned to India in the hope of complete recovery, because that was a wartime also. In 1919, the First World War almost completed, so it was over. So therefore, he returned to India in the hope of complete recovery of his health. Okay. But unfortunately, on April 26, 1920, Ramanujan died at the age of only 32. And there are probable diagnoses of Ramanujan's illness. Many these physicians there, they thought that Ramanujan might have suffered from tuberculosis, then severe vitamin deficiency, then liver cancer was one of the probable diagnoses, then lead poisoning due to not cleaning cooking vessels, because he used to cook himself and he was a pure vegetarian, and that was the Cambridge, that was a war-ration country then, England. So therefore, the food ingredients that was sent from Madras were not on time. So therefore, Ramanujan suffered a lot from food scarcity. But British Dr. D.A.B. Young in 1914, he made a careful examination of all extant records and recorded symptoms of Ramanujan's illness, because Ramanujan was also occasionally ill while in his second FA examination at Pachayappa College, dysentery type of infection. So he convincingly concluded that Ramanujan suffered from hepatic amoebiasis, not of tuberculosis. Okay, so it is a parasitic infection of the liver, and the illness is difficult to diagnose. It is very difficult to diagnose at the time, but sadly, once diagnosed, it can be readily cured. So one can say that Ramanujan was actually misdiagnosed of illness. Okay, the complete biography of Ramanujan was written by Robert Kenigel, the man who knew infinity, and this was actually made into a film with the same name, with Dev Patel as the lead actor as Ramanujan. And I have not seen this film because this Dev Patel cannot be Ramanujan in my eyes. Okay, so one can see if you are interested. Okay, so and there another this novel. This is a novel. There are many mistakes are there. Levitt Wilston, Indian clerk, but the actual the facts on Ramanujan's biography can be traced from Hardy's the book Ramanujan, 12 lectures, etc. Hardy's Ramanujan, and the obituaries written by Sheshu Iyer and others in Ramanujan's collected papers. Okay, so those are very readable accounts of Ramanujan's biography. And there are Ramanujan's notebooks. As I told you that Ramanujan initially did his all sums in slate, and later on only the final results he noted down in his notebooks. So Ramanujan left actually 3 notebooks. The first notebook was totaling 351 pages and contains 16 chapters of loosely organized material. Okay, and the remaining are what? Unorganized. The remaining material were unorganized. And the second notebook is a revised version, and it contains 21 chapters comprising 256 pages of this organized material and 100 pages of miscellaneous unorganized material. And the third notebook is very short. It is only 33 pages of unorganized entries. Okay, and in almost all, for all the results, Ramanujan never gave any proofs. So sometimes he sketches some proofs, but that is only one line or a hint type of thing. But he usually never did not record his proofs. And when Ramanujan's collected papers were published in 1927, Hardy thought that Ramanujan's notebooks will also be edited. Okay, but the editing was not completed due to some financial crisis of the society, London Mathematical Society. So the editing was initiated by Z.N. Watson and B.M. Wilson in the 1930s. But due to premature demise of B.M. Wilson in 1935, the project was never completed. Nevertheless, Watson wrote over 33 papers, over 33 papers on Ramanujan's work, Ramanujan's notebooks and letters, etc. Okay, and in 1957, Tata Institute of Fundamental Research, TIFR, they published the photocopy edition of the notebooks, but no editing was done. Okay, so if a page is blank, kept by Ramanujan, and in that photocopy edition also it was blank. So it was just photocopied. And Bruce Seaborn of University of Illinois at Urbana-Champaign, USA, he undertook the task of editing the notebooks in 1977. And with the help of his students, co-authors, and many others, so he completed this Herculean task by publishing 5 volumes, Ramanujan Notebooks Part 1 in 1987, Part 2 in 1989, Part 3 in 1991, Part 4 in 1994, and Part 5 in 1998. And the meaning of editing is that if a result in Ramanujan's notebooks is correct, then it is correctly said that this is the way of doing that. And also it has been, if it has been proved by others, then actual reference is given. And if it is not proved, that has been proved. And if it is incorrect, that is also been shown. So if we want to have Ramanujan's work, have a look at his notebooks, these edited volumes. Okay. And for the first 4 volumes, Barnes was awarded Leroy P. Steele Prize of the American Mathematical Society. And okay. So this is Ramanujan's mathematics. What type of Ramanujan's did mathematics? So you see that he did many things. For example, in partitions, okay, partitions, then mock theta functions, theta functions, then hypersymmetric series, many things he did actually, and these quadratic forms, etc. So, and he had this great contribution in pi. So let me now say about Ramanujan and pi. And just let me share it again. Just a minute, resume. Where is it? Oh, I have some. equations. Then just a minute, I'm just checking my slides where I have kept. Oh, this is not 33. Just a minute, 34. Oh, one 57. Wait, 157. Okay, so this has come. So now I want to talk about Ramanujan pi. Well, let me check. Dr. Sengupta, am I
Yes,
audible?
sir. Yes, sir. You're audible, sir.
Okay. So now I come to Ramanujan pi. So how many minutes I have left out?
Sir, you can continue for more than 15 to
Sir,
20 minutes.
15, 15 minutes we have, yeah.
Okay.
15 minutes.
Okay. Thank you. So, so this is some of Ramanujan's approximations. So you see that the other pi formulas given by the other mathematicians were not like this. So he approximated pi by these radicals. Okay. So these are his radical formulas. This one. So pi is 9 over 5 plus square root of 9 over 5. Pi is this one. Okay. So this value of pi is 3.141592653, etc. Up to this point, the value is correct. Okay. And these approximations actually came from his what is called class invariance. Class invariance. He wrote many class invariants, over 110 class invariants, and using those class invariants, one can actually approximate the value of pi. So in his famous paper, Modular Equations and Approximations to Pi, so after coming to England, he wrote this, it's his first paper, but almost all the results in this paper were actually done while he was in India. Okay. So in his paper, he gave the approximations of pi by using class invariance. Then there he gave 3 series for 1 over pi. This is for 4 over pi. This is actually 1 over pi. 4 I can take here. 1 over 4. Okay. Right. So therefore, these are series for 1 over pi basically. So he gave 3 series of 1 over pi, and he said that these are classical theory of elliptic functions. And he gave a brief proof of these results, how he found. But this was very brief, and there was many problems in understanding his theories. Okay, so I'll come back to that. And this series also appeared in a Disney film that is called High School Musical, and I suppose that you might have seen, some of you might have seen this film. So in this film, this is a bright student, Vanessa Hudson. Then the teacher is writing Ramanujan's series. You see, this is 4 over pi. And what is Ramanujan's first series? This is 4 over pi. Second series is 16 over pi. You see, this is 16 over pi. This one, 16 over pi. But what the teacher is writing? 8 over pi. 8 over pi. So this is a bright student, and in the picture, how they will show that she is bright, because the teacher is writing wrongly. This should be 16 over pi, and that has been corrected by the student. And the teacher is asking, is it? Is it? And then the teacher is checking her notebooks, and yes, this is corrected. And for that, there is a good job for the student. Okay. Then after offering the 3 formulas for 1 over pi in classical base, at the beginning of section 14 of his results, Ramanujan said that there are corresponding theories in which Q is replaced by this QR, okay, where R equal to 3, 4, 6. And the classical theory is about R equal to 2. R equal to 2. Okay. So from R equal to 2, he got those 3 series. He said like that. And he said that there are classical theories like 3, 4, 6, where R can be replaced by this. And from there, he got another series, another 14 series. And 2 series are for Q3, that means this cubic theory, and 10 are for Q4 theory, and 2 are for K6 theory. Okay. But without giving any proofs. He just said that this follows from those alternative theories. And this is Ramanujan's base 3, this is base 3, base 4, these are base 4, okay, and these are base 6, etc. And Ramanujan never returned to the corresponding theories in his published paper, but 6 pages in his second notebook are devoted to developing these alternative theories. Okay, the initial steps were taken by K. Venkatachalyengar of Madurai Kamaraj University of Madurai, and Professor Venkatachalyengar, he actually examined some of the entries of Ramanujan in alternative theories from those 6 pages. All the results on those 6 pages of Ramanujan notebook were proved only in 1995 by Van't, Vargava, and Garvan, and that is published in Transaction of American Mathematical Society. Okay, there they have actually developed Ramanujan's those theories as understood, probably as understood by Ramanujan, because Ramanujan have never given any hint how he developed. And 14 years after the publication of Ramanujan's epic paper, the first mathematician to address Ramanujan's series for 1/π was Chawla in 1928 and 29. Okay, so he found the proof of the first series. And Ramanujan's series were then forgotten by the mathematical community until November 1985, when R. William Gaspar Jr. he used Ramanujan's one of the series, this is the series, Ramanujan series, famous series, to calculate over 17,526 and 100 digits, 20,100. 17,526,100 digits of pi. And at that time, it was a world record. And Gaspar was not sure whether this is correct or not. Actually, he calculated the continued fraction expansion of pi over 17 million decimal places, and from there, he actually calculated the digits of pi. And he actually Gaspar compared his calculations with Kanada and Tamura. Okay, because I already told you that Kanada and Tamura, by using AGM formulas, they calculate over 17,700 something this million. Okay, over 16 million. So this was there. So they compared with Kanada and Tamura and Gaspar's formulas, and they found that Ramanujan's this is probably correct. Okay, and at about the same time in 1987, Jonathan Borwein and Peter Borwein, they proved all Ramanujan's series, and they published the book, the famous book Pi and the Azium, in 1987, where they proved all Ramanujan's 17 series by using not Ramanujan's technique, but some techniques developed later on. Okay, after Ramanujan's death. So therefore, the mystery was still there, that how Ramanujan might have developed his series. And in a subsequent series of paper, they found many other further series for 1/π, and one of their series yielding roughly 50 digits of pi per term. And Gaspar, the series used by Gaspar, that actually gave 8 digits per term. But this is found 50 digits per term for Borwein brothers series. Okay, and at about the same time as the Borweins were devising their proofs, another 2 brothers, David and Gregory Sudnowski, they also derived new series representations for 1/π. And in particular, the Sudnowskis used their series, this one. This is another famous series, and they calculated a world record of over 2 billion digits of pi by using this series. Okay. And in fact, the Mathematica, the programming Mathematica uses this formula to calculate the digits of pi. Okay. And in the last few years, further particular series representations of 1/π, as well as some other general formulas, were subsequently derived by several others. And one of the main architects was Heng Huat Chen of Singapore. He was one of the students of Bruce Barnes. Okay. And there are many other papers. I have not written all references here, but you see that these are many papers, and you see that this is last one by Wang Chung Chu that is in 2020, and he derived 4 of Ramanujan series by using a different method, a new method, and that is it is published only in July 18, 2020. So you see that still Ramanujan's these methods or series are giving interest to many other things. Okay. And there are many other super congruences involving Ramanujan series for 1 over pi. This is some of them. I just skipped those. And myself and Bruce Byrne, actually in about 2007, we systematically proved most of Ramanujan's original representation of 1 over pi and established a plethora of new series, including series for 1 over pi square. Okay, so actually what we did, he gave a hint for classical theory. So we took that hint and we developed Ramanujan's alternative theories and found series given by Ramanujan, as well as we proved many new series. Okay, and our papers were published in these are our papers. And our series, this one, 24 over pi square, this is the perfect analog of Ramanujan's series that was being used by Gospar. This is in a different notation, but that is the same series used by Gospar in his calculations of over 17 million decimal places of pi. So this is an analogous result for 1 over pi square. Okay. And there are many other papers, and our survey paper with Byrne and Chen, Ramanujan series for 1 over pi, a survey that was published in American Mathematical Monthly, that can be consulted for Ramanujan type series till the publication of this paper. Okay. Now there is another method or another famous or very well-known formulas. This is called BBP formulas. What is BBP type formula? So you see that we can find the billions and trillions of decimal places of pi by using those formulas. But suppose I want to find the individual digits, for example, 3.141592653, etc. Suppose I want to find, this is the this is 5, 6, 7, 8. This is the 8 digit. This is 8 digit. So now the question is, can I find the 8 digit? That means 5 without calculating this. Okay. Can I directly get what is the 8 digit of pi? 8 digit of pi, for example, or I can say 108 digit of pi. Okay, or 1 millionth digit of pi. That means individual digits. Can I find this extract? Okay, so that was a question, and people thought that it cannot be possible. Possibly cannot be possible, but Ramanujan gave some ideas. One can extract ideas from Ramanujan's series. And it is said that Ramanujan always helps in finding new formulas. So you see that this following series, this allows one to compute the billionth binary digit of 1 over pi, not pi, this 1 over pi, without computing the first half. That means we can directly calculate the billionth binary digit if one wishes, but that is a complicated method or complicated algorithm it could be, but this is possible by using this theoretically. So in 1995, David Bailey, Peter Boruin, and Simon Plouffe, they discovered a numerically astounding series, BBP, that is called BBP formula. What is the formula? This is the formula. So where is this formula? This one. This is their formula. So this is a very beautiful formula. This is not unlike Ramanujan or any other formulas. So this was numerically discovered, but it can be proved very easily. After knowing, it can be proved formally. Okay, so this is BBP type formula. So you see that using this, one can find individual binary or hexadecimal digits, because this is what, 16 to the power k. All right, 16 to the power k. So any this is a 16 base 16 number, base 16 expansion, like in binary expansion, decimal expansion. Okay, decimal expansion, say 235. I can write 2 into 10 square, and this 3 into 10 plus 5, etc. Similarly, there are for negatives also. Okay, 0.5. Okay, so something like this. Okay, so here this is base 16 formula, and this was used in 1997 by Fabrice Billard of France to compute what 152 binary digits of pi. Hello.
Excuse me, sir.
Yeah.
Hello, sir.
Hello.
Yeah, sir. 2 minutes, please. Yep. 2 minutes more. Hello.
Hello.
Yes, sir.
Yeah.
Yeah. Sir, you have 2 more minutes.
Okay. Oh, okay.
Yeah.
So in 2009, Daisuke Takahashi, he computed 2.5 trillion decimal places by using supercomputer. Then Fabrice Billard 2.6 trillion decimal places. Then Kundu and E, they calculated 12.1 trillion decimal places by using Sudnovsky's formula. Then 22.4 trillion, so it went on. Then last year, Emma Haruka of Google employee, she calculated 31 trillion, over 31 trillion. Okay, so she used Google Cloud virtual machines. And in January 29 this year, 2020, Timothy Mullikan set the current world record by calculating over 50 trillion decimal places. And that is the current world record. So that is the current world record that pi has been calculated that many decimal places. Okay. So that is the current record. So that is the current record over 50 trillion decimal places. 50 trillion decimal places. And there are many unsolved problems in pi. For example, is there any decimal? Is there any decimal BPP formula? BPP formula. Is there any decimal BP formula? That means, can I extract the decimal digits of pi individual? By BPP formula, we already know that hexadecimal and binary digits can be extracted. But how to extract decimal digits? That is not yet known. So this is an open problem. Okay.
Thank you, sir. Thank you so much for your insightful lecture. Now, I would like to ask the audience to ask any questions, whatever they have. So you can please unmute your mics and say, or you can just write into the chat. In the YouTube, they can also post their questions there. Any questions? So we'll be able to take 2 or 3 questions max.
Subhajit, in case there is no one else coming up, can I ask one question to Professor Baruah?
Yes, Father.
See the whole notion of measurement
Yeah.
of the infinity. I guess the application is going in terms of the galactical kind of, stars, and therefore applicable for physics. And I guess that's why physicists are as much interested in this calculation as I was trying to hint in the opening. So now, is the one? I have 2 questions. One, theoretical. That is, can mathematical calculation of measurement of the space be definitive, and can a formula like pi, as you are trying to explain, be a definitive tool for, and does it therefore contain a kind of element of certainty? This is one part of my question. And the other is, if so, does it mean that infinity is capturable by the finite mind?
Okay. So actually, now you see that this pi is irrational. So there are no end to it. The decimal calculation has no end to it. But what is the byproduct? That means what benefit we are getting from calculating so many trillion digits is that we are having some algorithmic progress. That means we have found some new formulas and new algorithms which can be used in other branches also. That is one problem, one thing. And second thing is that the sophistication of computers that can be measured by this pi calculations. That means if a new computer is built, supercomputer is built, then they use the algorithm for calculating the value of pi to test whether it is correct or not, because it is not a simple algorithm. So it involves so many other peripheries, other devices. So therefore, it is a very good test to test the applicability of those supercomputers when they are left to the market, etc. So actually, there is one application of this calculating trillions of digits of pi. Otherwise, in physics, actually, the physics people say that 39 digits are enough. 39 digits are enough to calculate, to measure the circumference of a universe, known universe, with an error of a hydrogen atom. Okay. So therefore, for them, this is immaterial. You calculate trillions or what? Okay.
But just a counter question. You
Yeah.
added that clause, known universe.
Yeah, known universe means
Yeah.
something that
Is already within
that
the
is
grasp.
known. Yeah.
Yeah. So does that itself not disqualify? Because can one presume that the universe that is known is the only universe?
No, that is different. But up to some level, it is well known. They are knowing that up to this it is known. Okay. So if we use up to 39 decimal places, then it will give very minimum this error in calculating the circumference. Okay. So that is what I mean.
Thank you.
Hello, sir. I have one
Hello?
question to you. Yes. Yes.
So that may be the case, the limiting value of this growth. So therefore, E is naturally coming there. But for pi, I think the pi and E have some connections, right? Definite connections. But I do not know exactly what you are asking for. But there might be something. But that is an approximation.
Achha.
But E naturally comes there because it is the initial growth or decay. So that naturally comes. Yeah.
And sir, I have one more, not a question. Just few years back, I read a article saying that now currently some mathematicians are using tau instead of pi, which is twice than pi. That is 44/7. I somehow read this article in the newspaper. Is it true, sir? That means people are using 44/7.
Yeah, that is just using. That means what? Instead of pi, they are using twice pi. That doesn't make any this difference to the mathematics. Yeah.
That means it will not create that much any problem.
No problem. Remember that 44 by this one is also this not pi. Okay. So that is a rational approximation. So and twice pi is also irrational. Twice pi is also transcendental, but theoretically it will not anything. There is nothing because it is just 2 times of pi. Yeah.
Okay. Thank you.
Hello, sir.
Yeah.
Hello.
Hello.
Yes, sir. Sir, I would like to ask that mathematicians, right from the Greek times, they were quite sure that pi is a constant number,
Yeah.
So they thought that they believed that the circumference divided by the diameter will always give us pi. So
Yeah.
how could they be so sure that it is always a constant quantity for all circles? Or did they
Because they knew it. One can prove it actually. One
okay,
can
there is
prove
a
it.
proof
Yeah,
for
yeah,
that.
yeah. There is a proof for that.
Okay, sir.
There is a
Okay.
proof. So because they also, but before proving, they noticed that mm, uh, the area is area divided by the square of the radius.
Yes, sir.
Okay, area divided by square of the radius,
Yes,
and
sir.
perimeter divided by uh, twice of the radius are same. They observed that. So that means
Okay.
what your pi r square and twice pi r, isn't it?
Yes, sir. Yes, sir.
So area is pi r square and perimeter is twice pi r. So therefore, they knew
Twice
that
pi r.
those ratios were also same. From there, they actually there is a proof. One can easily get that.
There is a
You
proof for
can
that.
get any book, even any pi
Okay.
book.
Thank you, sir.
Oh, I forgot to actually I mention the pi books. Okay, no problem.
Any other questions? Anybody else? Yes.
Sir, you can mention the name of the books now also, sir. You can mention the
Okay, I have
now
to
also.
again share. Okay, let me check.
No problem, sir. You can. I
Let
guess we
me.
have the time shortage, sir. To at least
Not
Okay.
much, not much.
one
So
minute for the
quickly.
sharing the book
Yeah, yeah.
link.
Yeah,
Just for
yeah, yeah, yeah.
this.
Yes.
Somewhere it is. Oh yeah, here I have. Oh, hello,
Yes, sir.
Yes.
hello.
Yes, sir.
Yes, sir. Yes, sir. We can hear you.
We can hear you, sir.
Actually, I left this on this Guinness Book of World Records, etc. So sometimes I'll tell you. Just the books are at last. These are the books. Okay, is it coming?
Yes, sir.
This is
Yes.
the first book on a history of pi. That was also mentioned by Father Peter Beckmans. Then this is Pi and the AGM by Boron Brothers. Then this is The Joy of Pi. And this is another, a biography of world's most mysterious number. And this is another book, Pi Unleashed. This is where the Makin type formulas were there. And this is another book, The Number Pi by American Mathematical Society. Then this is a pi source book where one can find various papers on pi, including Newton's paper also here. And this is the addendum to the pi source book, Pi, the Next Generation, where our survey paper is also there among the 25 most cited papers here. So Pi, the Next Generation. So that is the latest book. Okay. Okay.
Thank you,
Okay.
sir.
Thank you, sir.
Thank you, sir.
Any
Thank you.
any other questions? Anybody else? Anybody else? Any other questions? Uh, so I guess that's the end of the interactive session. Thank you so much. Thank you so much, Professor Nayandeep Deka Baruah. I would
Thank
like
you.
to take this. I would like to take this opportunity to thank for the principal, Professor George Tharathil, for his encouragement, for the Ajit Kurian for supporting us, Mr. Devdut Sengupta, my colleague, for being the co-convener of this one, Ms. Yadika Prasad for the technical support, Dhiru sir, Dhiru Subba for the technical support, our student Aditya Ghosh for designing the poster, and our beloved participants for whom this entire webinar was organized. Thank you so much. Thank you all. Have a nice day ahead. Thank you so much.
Thank you, Baruah, sir. Once again, thank you from my
Thank you
side.
all. Okay.
We'll
Thank
look
you, sir.
to hope you to see you in future in our
Okay.
college.
Okay. Thank you.
Okay, sir. Thank you.
Yes, most welcome, most welcome. Thank you. Bye.
Bye.
Bye. Thank you.